We're going to talk only about the limacons today, and there are 4 different types of limacons, so there's 4 different graphs that could be produced. We're going to begin with the equations and the characteristics, so it's going to work out very similar to what we did in the rose curve and the circle, where we list like, okay, what shape is it? What's the max R value? What's the number of zeros? There are some significant points, so we're going to see some similarities there. I would guess during your graphing investigation, you sort of accidentally graphed some type of limaçon when you were trying to make a snowman. So when you're trying to make a snowman, you could get 2 circles that were stacked on top of each other, but you needed that third circle, that third piece of the bottom to be like lower or higher. So I would guess you started adding or subtracting things, trying to move the circle, which we found out that can't happen. It's going to be attached to the pole. Okay. So you probably graphed some type of limaçon. Some of you might have gotten the one with the loop, and then others maybe you couldn't tell as well, like maybe it was the flat-sided one. Okay, we kind of drew up some different examples on the board. But later in the investigation, it actually has you do different ones. Okay, but I would say that's probably the first time you experienced it. Depending on which equation you're using, sine and cosine is going to determine your symmetry. So this is true for all of our polar graphs. If it's a sine function for circles, rose curves, or limacons, then it is symmetric to the vertical axis. Okay, so that's always true. If it's a sine, it's symmetric to the vertical axis. That's a nice check for you at the end to see, like, did I really graph it so it looks symmetric to the vertical axis? If I didn't, then I should recheck my graph. Okay, cosine will always be symmetric to your horizontal axis, or what we would call in this chapter like the polar axis. Okay. So sine and cosine will determine symmetry, and it's the same symmetry you saw with circles and rose curves yesterday. To determine the orientation of your graph, you're going to look at whether the equation is using the plus or the minus. So it's not like the equation will have plus or minus in it. It'll either be a plus b cosine theta.
All special education department teachers to the shield. I need all special ed teachers to the shield. Thank you.
Or a minus b cosine theta. So it's going to be one or the other. And I'm just going to write down really quickly a couple of things. Like if it was a plus b cosine theta, then the orientation of my limacon would be like to the right side of my graph. So it's kind of like the circle, like how we would say the circle was on the right side of the vertical axis. Versus if it's a minus b cosine theta, then it would be on the left side. Okay. Now there is one big difference between the circle and the limacon, and that's that the limacon will cross the vertical axis. So it's not like it's all going to be to the right of the vertical axis, but the majority of the limacon will be on the right side of the axis. Okay. And then for sine, it would be up and down. Okay, so if you want to add those, you could say a plus b sine theta is up, and a minus b sine theta is down. I think those are pretty intuitive for you. But I just wanted to be more specific about what I mean by orientation. A plus B determines your max R value. And when I say A plus B, I guess I really mean like almost like their absolute values. So if you had some limacon with equation like 1 minus 4 cosine theta, then to get your max R value, you would just do 1 plus 4, which was 5. So the max R value would be 5. So the negative value doesn't matter there. You're just really adding up the absolute values of A and B. Okay. And then the last thing that we need to know for these particular graphs is we'll look at the ratio of A to B and we'll check its value. It determines the type of limacon that you're going to graph. And I have here an image from page 751. So if you at least want to jot that down in your notebook so you know, like, if I need to see more specific stuff or I want to see that picture again, you can look at page 751. I would encourage you real quick in your notes to try to sketch the 4 different shapes because I'm going to label them. Okay. So try to sketch them. I think, like I said, limacons are kind of hard to graph, only because the way we plot our points, we don't always plot enough points to really get the round part of it. So you just got to keep it in the back of your mind, like this shape is supposed to be round-ish. Okay, so just try to keep telling yourself that when you're graphing on your homework tonight. Okay. So if I labeled these four, I call the first one a limacon with a loop. Then I have a cardioid, which has the word cardio, and that one looks kind of like a heart, doesn't it? Okay, so that's the heart one. And this one is dimpled, and this is convex. It does say their names down there, but I think that's kind of hard to read. Okay, so the dimpled one actually goes in a little bit, whereas convex is just kind of flat, like your basketball needs some air in it. To determine like what shape it's actually going to be, that's where you look at the ratio of A to B. So this limacon with a loop is whenever the ratio of A to B is less than 1. Then you have limacon with a loop. A cardioid is whenever A over B is equal to 1. So when you have the same, you're going to get the heart. Dimpled is when you have A over B, it's more than 1, so it's not cardioid, but it's not yet 2. So it's somewhere in between those two numbers, but not equal to either one. Okay, that's dimpled. And if A over B is greater than or equal to 2, then you get that convex shape that just looks flat on one side. So like you want to label that just like we did yesterday with the rose curve, like rose curve with 5 petals, rose curve with 12 petals. So we knew going into our graph how many petals we were going to make. You want to know going into your graph what shape you're going to try to draw. Now there's one other thing that I want to label there. It is how many zeros each of these limacons have. And remember that zeros in polar graphs are different than zeros on the rectangular plane or the Cartesian plane with the x and the y-axis. Always up until this point, zeros were identified as like where we cross the x-axis or the horizontal axis. In polar graphs, our zeros are only at the pole. So I'm actually going to start over here on the right with this convex shape. Notice that there is the intersection for the horizontal and the vertical axis, which would be identified as our pole, and a convex limacon will never cross the pole, so it has no zeros. So I'll write that down. No zeros. That is also true for dimpled. No zeros. Never touches the pole. And you can kind of see, like, it goes on the other side of the vertical axis, but the majority of it is to the right side. Okay, so that would be like orientation to the right. Okay. For cardioid, that like little point on the inside of the heart, that will always happen at the pole. So you just come in, you touch the pole, and you move away from it, so you have exactly 1 0. If it's cardioid. And then for the loop is kind of like when we draw the petals on the rose curves. In order to go through and create that loop on the inside, you're going to have to cross the pole 2 times. Once going in to make the loop, and then once to come out and draw the rest. Okay, so this guy has 2 zeros. Are you okay with that, how I counted the zeros just looking at the pole? Does anybody have any questions that I need to answer before we do an example? Okay, let's do an example. We've got r equals 2 plus 3 cosine theta. We're going to be asked to do very similar work that we were doing yesterday with circles and rose curves. There are a few differences today, just because, of course, we're working with a different function. When you're thinking about your quiz tomorrow, how will you be able to tell the difference between this and the circles or the rose curves? You've got plus or minus in the mix. So anytime we see a plus or minus, then we know we're going to have Limacons. And I would go one step further right here. I would do my A over B, figure my ratio. So A is 2 and B is 3. So I would figure 2 over 3. Thank you. And 2 over 3 is less than 1, so that classifies it as the loop. Okay, Limacons with loop. So I know I'm going to be drawing the loop. The max R value is 5. 2 plus 3. Yeah. And the number of zeros? 2, Lillian says. Anytime you have the loop, to create that inner loop, you've got to cross the pole twice.
Would it be okay if we just call the loop the shape?
Yeah, I probably wouldn't take off, but I do want you to try to remember the name Limacons. So I probably wouldn't take off for it. I'd be okay with it.
Okay.
But it is technically not like a loop. It's a Limacons. So, is that answered? Okay. Notice there's something missing here from yesterday. After we said the number of zeros, what would we have done yesterday? Find the zeros. Okay, I'm going to show you why you don't have to do that today. If I were to find the zeros here, I would do 0 equals 2 plus 3 cosine theta. I would subtract 2 and divide by 3. So I have negative 2/3 equals cosine theta. And then I would have to think about what angles have cosines of negative 2/3. Don't know, right? Could you answer that with a calculator? Yes. But remember, I expect you to be able to graph all the polar graphs without a calculator. So we can't answer that question exactly without a calculator. I don't really need to know what angle the 0 is at. Okay, the key piece there is that you know you'll cross at the pole. That'll be the intersection for the loop. So to do your significant points, then we don't have zeros to pick from the significant points. For all of my Limacons, I will just use the values from 0 to 2 pi going by pi over 2's. So it kind of takes us back to when we graphed trig functions and we did the frame. Okay, I'll just sort of use those 5 points. So in my significant points, I'm going to start at 0. I'm going to do pi over 2. I'm going to do pi, 3 pi over 2, and 2 pi. Okay. This is kind of helpful for me because it gives me more points to help me graph my Limacons. And then also at the same time, the angles that I've chosen are very easy angles to evaluate sine and cosine for. Because if you're doing those quadrantal angles, sine or cosine is going to be 0 or 1 or negative 1. And that's really easy to calculate. We won't have to mess with like radical 2 over 2, stuff like that. So let's plug those things in. Let's start with 0. 2 plus 3 times the cosine of 0. What is the cosine of 0?
1.
1. So that's 2 plus 3 times 1, or 5. Okay, there's my max R value. Put pi over 2 in. 2 plus 3 times cosine pi over 2. What's the cosine of pi over 2? 0, so then it's just 2. Pi. Cosine's value is negative 1 because you're going to the left. So we're doing 2 plus 3 times negative 1, or 2 minus 3, which is negative 1. So that's giving me an R value that is negative, meaning when I try to graph at pi, I'll go opposite, actually towards 0. Okay. 3 pi over 2's cosine value? 0, so we're back to 2. And then 2 pi is really the same thing as 0, so we know it should be 5, and if you calculated it is. Okay. These give me 5 polar coordinates that I can plot. Okay, so remember, figure out what ring you're on and where the angle is, mark your point. So 5, 0. Go out to the 5th ring, plot a point at the angle 0, which is on that polar axis. I'm going to label this right here as 5, 0. You don't have to label your points on your graph. I'm only doing that so you can kind of help see why I'm putting the points where I am. My next point is 2 pi over 2. Go out to the 2nd ring, pi over 2, plot a point. -1 pi. Go to the 1st ring, 1st circle, and then pi is to the left, but since my R value is negative, I actually want to plot in the opposite direction towards 0. So this is going to be -1 pi, right in there. That point for my limacon is going to be like the inside edge of my loop, okay, because the other part of the loop will cross at the pole. That's kind of like how far the loop goes in. And then 2 comma 3 pi over 2 down here, and then I'm back again to 5, 0. So that's where I'm going to complete my limacon. Now, when those points are plotted, it doesn't really look like you can't just connect the dots. So you have to remember what shape it is. It's a limacon. It should be round, and it's limacon with a loop. So even though we don't know what the angles are, we do know it's crossing here at the pole, right? Okay, that's where we want that to go through to kind of create that little loop on the inside. So for me, it's probably easiest if I kind of start and make my loop. Okay, so I usually start in the loop, and then I'm going to come out. I'm going to try to keep it round. Just keep telling myself, keep it round, Miss Cronky, keep it round. Okay, not bad. Any questions, concerns? Okay, I'm going to put one more up so you can kind of look at it and see if you can figure out some of these things and maybe get some of the significant plots going for us, significant points. This is r equals 4 minus 4 sine theta. Based on the equation, it's definitely limacon. Maddie, were you able to decide which type it was?
I wasn't.
Oh, what was troubling you about that?
That 4 is negative. I wasn't sure if that was part of the equation or if that was part of the number.
Yes, so like when I have you do like max R value and I say A plus B, remember I just mean really like the absolute value of A plus B. So when we're doing the ratio of A to B, that is a great question. Same thing. Just look at it like the absolute value of A and B. So then we would say it would be like 4 over 4. Okay. So 4 over 4 is equal to 1. That means it's a cardioid, so it's going to be the heart shape. Okay. Whereas if you kept that negative, then you might want to call it like limacon with a loop, because then you would get a ratio of -1. So the ratio, I guess I should clarify, should always be a positive ratio. So you're always looking at just the absolute values of A and B. Okay. What is the max R value, Katie? 8. Yep, 4 plus 4. And again, we're not going to keep that negative with that 4. Okay, that's just telling us that its orientation is down. Okay, so most of it will show up below the horizontal axis. The number of zeros, were you able to get that, John? 1. If it's cardioid, it has 1. Okay, and we don't have to find the number of zeros. Okay, we might be able to find the number of zeros on this one, or where the 0 is, but you don't have to find where the 0 is. And then for significant points, just like I did on the last one, I would use the same 5 values. So 0 to 2 pi, go by pi over 2. Reason being, those are going to be the easiest to calculate for sine or cosine. Okay. So now we're doing 4 minus 4 sine theta. Sine of 0 is 0, so that's just going to give us 4. If I plug in pi over 2, the sine of pi over 2 is 1, so that's 4 minus 4 times 1, which will be 0. Pi, the sine of pi is 0, so that's 4 minus 0, which is 4 again. 3 pi over 2 gives us a -1 for the sine value. And so then we do 4 minus 4 times -1, which is really 4 plus 4. And there's the max R value that Katie gave us. So the max R value should be somewhere in your table. Okay. And then when you get back to 2 pi, that's really the same thing as 0, so we should be back at 4. Notice that in this table, we actually have found the 1, 0. Okay, whenever the R value is 0, you're at the pole, so we just found where that 0 was. Okay. I would plot those points, 4, 0, 0 pi over 2, 4 pi, and 8, 3 pi over 2. So I'm going to kind of run off and just label it down here. And then back to 4, 2 pi. That's that 0.40. So remember, this guy here at the pole, this is where I sort of get that heart shape. Okay. And then I just try again to keep it round. Okay, as best I can. Okay. This one is going to be kind of oblong in my picture. Oh, I probably should have went more over. Yeah. I admit, I'm doing pretty good on this today.
What are these used for? Like real world kind of stuff?
That is a good question.
Or are they just like something that was found, so they decided to talk about it? It's like finding out dirt pebbles are actually random shapes. Why does it really matter as long as you, I don't know, grow flowers?
Yes, it's good for telling.
Did you say random shapes? Okay. I misheard you.
I guess it's good if you want to tell someone how you help them, just like great practice.
Yeah, it is kind of nice.